Language model processes tokens. These are discrete units of text, whereas images are continuous grids of pixels. For an example, a colored image of 224 by 224 size will have 150k numbers. These are completely different modalities. How do you connect them? Hello everyone, welcome back to my channel. Today we are going to understand how modern vision language model works, from the raw pixels to the model response. We have already covered the Scratch implementation of vision transformers in one of our previous videos. Today we are going to see how we use them in LLM inference. So let's get started. So the most common approach to a multimodal inference is vision encoder, a neural network that converts the image into a sequence of vectors that a language model can process. Here are the steps to do so. Step 1. The image is divided into a grid of fixed size patches, typically 14 cross 14 patches or 16 cross 16 patches. An image of size 224 by 224 with the 14 cross 14 patch gives you around 256 patches. Each patch becomes a small image fragment. In step 2, that is patch embedding, each patch is flattened into a vector, like for example 14 cross 14 cross 3 will be equals to 588 numbers, and projected to the model's embedding dimension, example 1028 or 1280, using a linear layer. And then we add a positional encoding, so the model knows where each patch came from the original image. And finally, the patch embedding flow through a vision transformer, essentially a standard transformer encoder. After processing, each patch position has a rich contextual representation that captures not just patches raw pixel, but how it relates to surrounding patches. The most common vision encoders used in VLMs are Clip VIT by OpenAI, that is trained on 400 million image text pairs, and it is most widely used. Second is SIG LIP by Google. It is improved clip with sigmoid loss, so it is better at fine-grained understanding. And third one is Dino V2 by Meta. It is self-supervised, no text supervision. So it is strong at spatial understanding. And next, the connecting vision to language, the vision encoder output is a sequence of 256 vectors in the vision embedding space, the previous step we just discussed. The language model works in its own embedding space, that is typically 4096 dimension for a 70 billion model. So these two phases are different. You can't just concatenate them. You need a projector to bridge the gap. So there are three approaches to do so. The first one is MLP projector. It is the simplest approach, like a two-layer MLP that maps each vision encoder output vector to the language model's embedding dimension. So for example, like a 256 vision vector will be mapped to 256 visual token in LLM space. These visual tokens are then prepended to the text tokens. The language model processes them all together with standard attention. So the pros are like it's simple and it works well, but the cons are 256 visual tokens consume a lot of context length. So the second approach is a Q former, that is also called the blip2 approach. So instead of mapping all 256 patches, use a small transformer with Q learnable queries. Tokens that attend to vision encoders output. So for example, a 256 vision patch will be mapped to 32 query vectors that will give out 32 visual tokens. This compresses the visual information from 256 tokens to 32 tokens, much more context efficient. The third one is perceiver resampler, or the flamingo approach. It is simpler to Q-former but more flexible. So in this, a cross attention mechanism between learnable queries and vision features is established, and it handles variable resolution images naturally. Now we move on to the cross attention method. Like once the visual tokens are in the same embedding space as the text tokens, they participate in standard self attention together. So this means that a text token can attend to visual tokens, like what color is the object I'm describing, or visual tokens can attend to the text tokens, like what aspect of the image is being asked about, or visual third is like visual tokens can attend to each other. That is a spatial relationship. This cross-modal attention is what allows the model to like ground its language in visual context. For example, when answering what color is the cat's color, the color text token attends uh, to strongly to the visual tokens corresponding to the color region. Those visual tokens contain color information from the raw pixels, and the model synthesizes it like it's either red or blue. The attention mechanism doesn't need to know about modalities here. It's just operates on sequence of vectors. So adding a vision is a simple as adding vectors to the sequence. Now, here is a question like, what about high resolution or multi images? Because standard transformer with 224 by 224 dimension input misses fine details like reading text in an image, counting objects, understanding charts. These need higher resolutions. So we have certain techniques like dynamic resolution. This splits the image into overlapping tiles, each 224 by 224 or 336 by 336. Encode each tile separately, then concatenate all tile tokens. So an image of 124 by 124 dimension might become like 4096 visual tokens. This captures fine details but uses a lot of context length again. So the second technique is dynamic tiles or any rest you can say. This adapt the number of tiles, the image's natural aspect ratio and the detail needed. So a portrait might use 2 cross 4 tile and a landscape might use 4 cross 2 tiles. And the third one is the multi uh, image support. Like some tasks need multiple images. What changed between these two photos, or code editing with like before and after snapshots. Most VLMs handle this by simply concatenating the visual tokens like from multiple images with separated tokens in between them. Now again one more challenge came, like the video, what to do with the video and the audio. So video is just a sequence of images like frames. The naive approach, that is encode each frame as a 256 individual visual tokens and concatenate them. So a 30-second video or at 30 frames per second will give you 900 frames times 256 tokens. That is 230,400 visual tokens. Those are way too many. So the solution to this problem is temporal subsampling, like use 1 frame per second instead of 30. Temporal compression, like encode temporal differences rather than full frames. Or pooling, like average visual tokens across nearby frames. Or finally, like video specific encoders, train encoders that understand temporal dynamics, like video MAE or video Dino, for example. And the second challenge that we discuss is the audio, like how we can process the audio. So audio can be converted into a spectrogram, like a 2D image of a frequency versus time. and processed with the same vision encoder pipeline that we have been using so far. Whisper by OpenAI uses a vision transformer style encoder on MEL spectrograms. The output gets projected into the language model's embedding space. This is how models like GPT-4o handles audio. Like it's all just patches of different modalities being projected into the same vector space. Now we have few challenges with inference for VLMs. Like multimodal inferences introduces a specific engineering problems or challenges. First one being a visual token count. Like a 1024 cross 1024 images will be equal to 4096 visual tokens. Those are like huge numbers. Each visual token occupies kV cache memory like a text token. So long image conversation can exhaust our kV cache quickly. And the second challenge is like vision encoder compute. Like running vision transformer on high resolution image is pretty expensive, and it can be parallelized with text prefill, but it adds latency. So the solution is you cache vision encoder outputs separately from text kV caches. The third one is like dynamic sequence length. This is the third problem. Like for example, text only requests are short sequences, but image requests are suddenly 256 to 4096 extra tokens. And this makes like batching harder, like very uneven sequence lengths. So the solutions in production are like vision encoder runs asynchronously and results in pre-cached, and visual tokens compressed with Q-former or pooling, we can do that. And the third solution is like you should do image specific prefix caching, like same image in multiple turns. So to summarize this, the key insight of multimodal LLM is elegant. Like if you can express any modality as a sequence of vectors in the same embedding space, the transformer's attention mechanism handles everything else. So image becomes patch tokens, audio becomes spectrogram tokens, and videos becomes frame tokens. The language model doesn't care, it just attend over vectors. For it's those are like numbers. So this is all about how you handle multimodal inference. In the next video we will discuss structured output and evaluation, like how do we get models to reliably output JSON, and how do we actually measure if a model is getting better. Thanks for watching. See you next time.